Right, can we see? Yeah, okay, so let's get started. Well, actually, let me just take the attendance one and think of it. Have I got what TV? Yeah. No, has that? David? Sabrina? Ray? Yeah. Barack? Yeah. Priscilla? Yeah. Patrick? No. Joshua? Yes, he's right there. Vanessa? Umar? Anna? Hussein? No. Dasha? Ishpreet? And Mo? And is David's bag here? It is. And I found. Fine. Okay, so can you write that down? We're having a look at this now: expectation and variance. Nikita, come on. Nikita, why am I asking? That is your bag of carrots, isn't it? Like, it's not like it's anyone else's bag of carrots, right? Would you mind cleaning it up, please? No, look, there's some still on the table. Thank you. I was about to ask whose bag of carrots that is, as if it could be anyone else's, but your bag of carrots. Okay, so, continuing now. We're having a look at what's called expectation and variance. Now, the first word, you kind of have an understanding of it already, just, the value you would expect, what you expect to see, like a future value, almost, okay? I'll give you an example, a very, very simple example. If you have a die, and it's labelled, 1, 2, 3, 4, 5, 6, and you roll it, you know, of course, that your x that you get can be any number from 1 to 6 then. Now, you might say, if I keep rolling it, I could calculate something like the average. So maybe you get something like 1, then you get 6, then you get maybe 1 again, and then 2, and then 6, and then 4, etc., etc., etc. If you think you do this long enough, and you were to get the mean average, what do you think you'd end up getting? Would you expect it to be something like 6? No. Or 1? No. What type of value would be you expecting? Somewhere like 3 or 4, isn't it? So you expect the mean to be 3.5 in what you might call the long run. Okay. You see this a little bit in biology, where when you were, we haven't done genetics yet, but you all kind of had the example of, what was it, like A, wasn't that it? A, then you get that and that and that and that. So, oh sorry, I did one wrong, didn't I? This one here, which is the same as that one there, isn't it? What percentage of the children will not have the dominant A display itself? Just 25%. Now, if the parents have 4 children, you expect one of the 4 to be this one, right? Will it? Yeah? Will it definitely be one of the 4?
No.
No, because sometimes it could be 0, Sometimes it could maybe be 2 or 3. Or just out of dumb luck, it could be all 4 of them. Okay? So the idea behind expected value is you try to put a number on what you think the future will be, but of course you know it won't really be that value. In fact, is it even possible to get 3.5 here? No. No. But you're just putting a value on the future prediction. Do you understand? So precisely what is the definition of expected value? So here the definition is the expected value of outcome X. All you do is you add up all the values of X times the probability of getting that value of X. So the example with the dice would be the expected value for the dice, the die, would be 1 times 1 over 6 plus 2 times its probability, 1 over 6, etc., etc. And what would be the last one here? 6 times 1 over 6. And in total, this will give you 3.5. Okay? Let's do another simple example before we look at more complicated ones. So I'll give you, yeah, question?
So I just repeat the definition. The expected value equals to the sum of values multiplied by probability
Yeah.
values.
Yeah. I'll give you a simple example. Let's say X could be minus 1, 0, 1, or 2. And then the probabilities of getting minus 1 will say 1 over 5, 2 over 5, 1 over 5, and 1 over 5. So I can kind of roughly tell the answer will be maybe about 1.2, something like this. Very quickly, using your calculators, can you calculate the expected value of this situation? Is it 1? Now remember, you were nearly asleep 5 minutes ago, so are you sure?
Maybe yes.
Maybe yes. Okay. What is it? What? 2 over 5. Is it that small? Okay. So it should be minus 1 times 1 over 5 plus 0 times 2 over 5 plus 1 over 1 over 5 plus 2 times 1 over 5. These cancel. That's 0. So yeah, you're left with much less than I thought. 0.4. Fair enough? Yeah? Okay. Can I scroll down? Can I scroll down, David? Yep, okay. I'll give you 2 more simple examples before I go on to the next idea. So, let's say this is minus 1 and 1, and this is a half and a half. And this one will say minus 100, 0, and 100. 1 over 3, 1 over 3, 1 over 3. Okay. So I want the expected value of x and the expected value of y. So for x, it's 0. And for y, it's 0. So in both games, you can see that you get the same expected value. But you wouldn't say both games are the same. In the first game, you could gain 1 point or lose 1 point with equal probabilities. In the second game, you could be sometimes with no points, sometimes with 100 points, and sometimes with minus 100 points. So you wouldn't say they're the same game, even though they have the same expected values. So there's something about this game that's a bit different to the first game. What's kind of different about this one? Yeah, the possibilities seem to be broader, don't they? Compared to this. So we need this other calculation, which is what's called the variance. Variance, yeah. Now, I think the easiest definition of variance is one that's going to remind you of something you've done before. It's going to look a bit like standard deviation. Tiny difference. The variance of x is the expected value of x squared, like this, minus the expected value of x then squared. Now, what does this really remind you of? Been a long midterm break, huh? I'm glad that this reminds you of a formula. Which formula? That's funny, isn't it? That the variance formula reminds you of the variance formula. Thank you, David. Standard deviation. Yes. Except there's one key difference between this and standard deviation formula. There's something that the standard deviation formula had. Yeah, what is it? The root. So, if anything, variance is a bit like the standard deviation squared. So, you can see that variance has to be positive. Just the same way standard deviation has to be positive as well. Let's have a look at an example, okay? Let's go back to the two examples up here and calculate their variances. So for this one here, I'll need the expected value of x squared, like this. So that would be 1 times a half plus 1 times a half, which equals 1. And then I need this one. What will this one equal? Well, yeah, it'll be 0. So what does the variance of x equal? 1. Now let's look at the example for y. The expected value of y squared will be, let me see, 10,000 times a third plus 0 times a third plus 10,000 times a third. What's that? 6667 roughly. Okay? And what's this one? 0 again, isn't it? So what's the variance of y? 6. Yeah. Now you can really see a big difference between the two games. In the first game, the variance was, 1. And in the second game, the variance is 6,667. Yeah. Can I scroll down? Okay. I haven't really talked about what x and y represent. It doesn't really matter too much what they represent. They just represent a value. But one common thing they could represent is money. Can I scroll down? Variance.
Yeah.
Oh, definitely, yes. Okay, can I scroll down? Yeah. So let's say you have a simple game. Let's say you pay €1 and two things could happen. You've got, let's say, a 1% chance of winning €10. and then let's say a 99% chance of not winning anything, €0. If I was to put this into a table, XP, the first one 0.01 and the second one 0.99. In the top situation, let X represent your net money. Does everybody know what I mean when I say net money? Is that a word you know? What does net mean here? Yeah?
The final price.
The final. Yeah. The end of day final position. So in the top situation, what would be your net money? 9.
Yes.
Yeah. And in the second situation, what would be your net? -1. Okay. So, yeah? How what?
Oh yeah, I'm not alone.
Yeah. Yeah. Okay. It's a good thing this is a class of doctors, not accountants. Right, okay, so can you calculate for me the expected value and the variance for this one? Expected value and variance. What's the expected value here? I expect it to be negative. -0.9? So minus 90 cent. And the variance then? So the variance will be 81 times that plus 1 times that minus 0.9 squared. So what do you get for the variance? No.
What is it negative?
It's 9 times this plus minus 1 times this.
We're not squaring.
Or variance now. $0.99, is it? Could be. Do we have the variance yet? 0.99? Yeah, I'll go back. So the expected value will be 9 times 0.01 plus minus 1 times 0.99, which is minus 0.90 euros. Okay, and the variance will be 9 squared times 0.01 plus minus 1 squared times 0.99 minus 0.9 squared. What is it in total? So this is 0.81, isn't it? Plus 0.99 minus 0.81. So 0.99. So how come the guy without a calculator gets it right? 0.99? Yes? What's the unit here? Is it euros? Not quite. Not quite. What is it? Euro squared, yeah. And you might say, well, it's kind of difficult to interpret the meaning of euro squared. So often the square root of the variance is used. It has a bit more meaning to it. So I think the square root of 0.99 is probably 0.995, is it? 0.995 euros. Yeah. Now the reason I'm doing that is because I just want to give you yeah.
Wouldn't it be plus 0.81, so this is minus, like the minus 0.9 minus that, wouldn't it become a plus?
This minus, when you square it, what does it become?
This is square.
Right. So a little bit of interpretation. Basically what you're saying with this game is, if you were to play this, are you expected to win or lose money? Lose. How much? 90 cents. Now, what's interesting is, again, is there any outcome where you do lose 90 cents?
No.
No. But this is just the value you would give to playing one turn of this game. You lose 90 cents per turn. It has a little bit more meaning if you were to say, what would happen if I played this game 10 times? So if I played this game 10 times, I would lose 9 euros in total. If I was to play this game 100 times, I would lose 90 euros. Because on average, how much am I losing each turn? 90 cents. But remember, that's only an average. There's not an actual outcome where you lose 90 cents.
Or more.
Yeah, sometimes you could lose more or less gain, etc. This square root of the variance represents a sort of a standard deviation. So what you could say is you expect to lose 90 cents per turn. On average, with a variation, and a pretty big variation too, because sometimes you could lose as much as €1, and sometimes you could gain as much as €9. Positive gain then. Yeah. So this just gives us our next idea. What do we mean if we say a game is fair? And it actually, fair has a meaning here. Does anyone know? Yeah, it's something to do with the expected value. What value would it have? Yeah, 0. So this means the game is fair to both players. For example, here, this game is not fair to you because on average you lose how much? 90 cents. It's also not fair to me because on average that means I'm gaining 90 cents if I'm playing this game, if I'm hosting this game. Okay. The only situation where the game is fair to both players is if the expected value is 0. That means the person hosting the game doesn't win or lose money, and the person playing the game on average doesn't win or lose money. Yeah? So, let me see. Many of you been to a casino before?
Every night.
Yeah? Yeah. I know some of you are coming from countries where casinos are probably quite illegal, but other people, yes. So, I've unsurprising news for you. Every game in the casino has this feature. So So what is that telling me about every game in the casino?
Unfair.
Yeah, you're expected to lose money on each turn every time you play. But there is one game where you're expected to lose the least money, at least. Does anyone know which game that is? The roulette wheel is the only game where you're expected to lose the least money on it. So I'll just give you one more calculation to do. In the roulette game, you have to bet on whether you get black or red. How many numbers on it? 30, 32, is it? That was 38 or 9. You're doing a quick Google there? Yeah.
Six.
36. So you have to pick a colour. Does 36 include the 0? Does it go up to 36 and there's 0, 0?
Zero is like 91. From 0 to 76.
Yeah, okay, good. So what happens is you pick a colour, red or black. There's 18 of them which are red. So you got an 18 out of 37 chance of getting it right. An 18 out of 37 chance of getting it wrong. But one of the colours is 00, which means it doesn't matter if you pick red or black. If it lands on 00, everybody loses. And that happens once in 37. So let's say you play a euro. If you call the right colour, you get your euro and an extra euro. So in total you gain €1. If you call the wrong colour, you lose €1 in total. And even if you call the right or wrong colour, it doesn't matter. If it lands on 0, you automatically lose. Okay? That's the probability, that's X. Give me the expected value of your turn here. Yeah, what's that as a decimal? 0.029 or something?
0.027.
27. So that's roughly 3 cents. That's not actually too bad. It means on average you lose 3 cents per turn, which is not too bad. Yeah. Some people go to the casino and play only this because you get free drinks. So they would consider this 3 cents the price you pay just to get a free drink. So it's actually a good deal then, if you think about it like this. Yeah. Although I don't think they would let you bet only €1 per turn. I don't know. I'm sure there's a minimum amount of maybe €5.
So it's still
Not 50.
beneficial
No.
for casino.
Huh?
It's still beneficial for casino.
It's still beneficial for the casino. And you can see why. It's only because of this, isn't it? What would happen if this wasn't here and instead this was 18 out of 36 and 18 out of 36? It'd be fair then. Neither the casino or you would be making or losing money. But because of the 00, this extra piece here, this is what's making it still negative. Yeah? Okay, do you understand this? This is not too difficult of a lesson. Let's see which ones I'll have you try. Yeah, 1 to 5 is enough if you want to try 1 to 5 now.
1, 2, 5. Okay.
Can I close this? Yeah.
Is it possible for you to zoom out as much so it will be the full lesson?
Can you still read it?
No,
first one?
Yeah.
Like
yeah.
the very beginning?
Yeah. No, like overall.
Ah, what are you trying to do, man?
It's already.
Want me to zoom out?
Yeah, a bit. Like now. Yeah,
Yes?
it's perfect.
Scroll down.
Yeah. Please. This one.
Okay.